Yeah. That's it. So intake. Wow. There's some cases. All right, it's 3 o'clock. Let's get started. All right, good afternoon, everyone. How's everyone doing today? Good, hanging in there. You know, it's a slog of a summer. Okay, so just like I promised, I finished grading your midterm ones. I have them here with me today. I'll give them back to you guys during the break. Average on the exam was almost perfect. It was about 37 and a half out of 50, which is 75%, which is good. So yeah, overall, I think you guys did well. So midterm two coming up already. It's next week. Although for this class, that seems like an eternity just because of how quickly the summer goes. But just next one coming up. So if you didn't do as well as you would have liked on midterm one, remember midterm two. It's your chance to make it up because remember the way I grade the midterms. Whichever midterm that you score higher in, I'm going to count that one as a higher percentage of your grade. And so if you did really well on midterm one, then that's, money in the bank. And so, you don't have to kind of, worry as much about midterm two. But if you didn't do as well this time, then you have time to make it up on the next midterm, which is going to be next Thursday. Okay. Yeah, but overall, I am very happy with how you guys did. You guys did. The spread actually was not that much too, compared to normal classes. And so, yeah, overall, very, very. Okay. All right. So the plan for today is we're going to continue on with our lecture notes on Reynolds transport theorem and control volume analysis. And so last time we were here, we had kind of that half lecture after the midterm. We introduced the concept of conservation of mass using Reynolds transport theorem. So we will continue with that. We'll talk about moving and deforming control volume today. That'll be the first order of business. And then we'll move on to conservation of momentum. Okay. And if we have time after all of that, then we'll start conservation of energy. But conservation of energy we're not supposed to get to until tomorrow. So plan for today is at least get through momentum, and then as much as we can get through energy, we'll get to that one. Okay. All right, and so remember, homework 3 is out there right now. So I did post that end of last week. It's all on control volume analysis, and so you should be able to get started on it, especially after today. After today, you'll have most of the control volume stuff. Homework 3 is due this Sunday. Okay, so just make sure you guys are working on that. It is fairly long. So there's actually 6 problems in homework 3. So don't save it all for the weekend. Otherwise, it's going to take you a long time. So after today, I would for sure try to get started on homework 3. See how far you can get. I think you can do almost everything. I think there's only 1 or 2 problems on there with conservation of energy. So after today, you should be able to do most of it. Okay. All right. Any questions I can answer before we get started for today? Question. Yes. Since homework 3 is due Sunday, does that mean we will learn next Tuesday won't be on the exam? Yeah. So I'm thinking for midterm 2 is going to be all control volume analysis stuff, and so this Thursday will be the last of what you need for midterm 2. Yeah. And then everything we cover next week, and then the week after that will be on the final exam. Yeah, so I'm not going to do the same thing I did for midterm 1, where we had just that one homework assignment due the night before the midterm. I realized that was kind of a poor decision. So homework 3 we'll do this Sunday, and then homework four will be the last homework. It'll be due on the next Sunday after that. Yeah. All right. Any other questions before we get started for today? Okay. All right. So let's go ahead and get started. Okay, so last time we were here, last Thursday, we talked about conservation of mass with Reynolds transport theorem. So we did a couple examples, fairly straightforward examples with fixed control volumes. Right? And so today we're going to build on that, and we're going to move on to moving and deforming control volumes. Okay. So we'll start with moving control volumes. That one I think is the one that's a bit more interesting. The problem on your homework also has a moving control volume. And then we'll move on from there. Right. Okay, so to kind of start, sometimes you'll come across certain situations where it's just a lot more convenient to have a moving control volume. Right? It may not seem that way because I think people typically find these types of problems very confusing. But trust me when I say that when the control volume is moving, it just naturally fits with some certain situations. Okay. All right. So the part that gets confusing is that we do have to adjust our Reynolds transport theorem to account for the moving control volume. Okay. It's a small adjustment. In fact, it's only an adjustment just on the flux term or the inflow and outflow term. But I think this does trip people up a bit. Okay, so I'm going to write out the Reynolds transport theorem again, and then I'm going to highlight the part that we're going to adjust. Okay. All right. So just to kind of remind you, for conservation of mass, we have basically two integrals or two terms that we have to compute in our Reynolds transport theorem. We have our accumulation / depletion term. Right, so this was the term with the time derivative. So actually, this term does not change at all. So this term stays the same with the moving control volume, thankfully. Right, so remember this term was partial t of integral of the density integrated over the volume. Okay. Right, so anytime we have a buildup or we have a decrease in mass of fluid mass within the control volume, this term will be active. But if our term is steady state, remember we assume that this term is 0. So remember, when you're doing these control volume problems, look out for that keyword steady state. And so when you see that word steady state, then any time derivative, can be assumed 0. And this term here is the only time derivative. Okay. All right. And so that's our accumulation term. So that stays the same. That's the same as what we did last week. Right. The other term in our Reynolds transport theorem, and this is the term that often transforms itself into multiple terms, depending on how many inlets and outlets that we have. This is our inflow outflow term. All right, so this term here was integral of rho times the velocity dot product with the normal vector dA. Okay. Now the adjustment that we're going to make here is the fact that when you have a moving control volume, the velocity that you're computing at the edges is no longer the absolute velocity, but now has to be the relative velocity of the fluid leaving the control volume from the perspective of the control volume itself. Okay. Now that's a lot of words, but mathematically, the way we do that is we simply just take the difference. Right, where v here, this is our fluid velocity in a fixed reference frame. So basically, that's the velocity of the fluid that you observe if you're on a fixed reference, right? So you're kind of just standing still, you're not moving with the control volume. And then this VCV here, this here is the velocity of the control volume itself. Because remember, the control volume itself is now moving. Okay. All right, so that's the big difference because in the previous version of Reynolds transport theorem, that term right there was just the fluid velocity because our control volume velocity was 0. It was fixed. All right, so we're going to take the dot product of this difference with respect to the normal vector of the control volume, dA, all this is equal to 0. Okay. All right, so that right there, that's the main adjustment that we have to make. It's just this term right here. Okay. All right, so to summarize it with words, for moving control volumes, we replace so for moving control volumes, we're going to replace the fluid velocity in the inflow slash outflow term. Okay. We are essentially replacing that with the relative velocity of the fluid as it leaves the control volume from the perspective of the control volume itself. Okay. All right, so remember we're formulating this Reynolds transport theorem from the perspective of the control volume, right? And so we have to account for that as we are doing our calculations, right? So whatever velocity that we experience as part of the control volume, we have to account for the velocity of the control volume as well. Okay. So it is a bit confusing, and these are the types of problems I think where you really benefit from seeing lots of examples. I only have one example here for conservation of math, but I do have another example for moving control volumes in momentum that I do want to get to today as well. Okay, so for these ones, the wording can get very tricky. Just try to keep on top of what's an absolute velocity, what's a relative velocity, the velocity of the control volume. And I will warn you now, it'll get even more confusing with momentum because we have momentum velocities that we have to take account for as well, right? So I think this is the part where fluids, I think it gets quite confusing for people. And so, it's really important to kind of stay on top of all the details, write everything out that you need to. Otherwise it can be just very confusing. Okay. All right. Any questions on this before we jump into an example? Yes.
So how come for this there's no production term?
Yeah, because right now we're doing conservation of mass.
Oh, okay.
Yeah, so there's no for conservation of mass, we assume that there's no production of mass there. Yeah. Once we get to momentum, there will be a production train. Good question. Okay. All right, so let's go ahead and do an example. Okay, so one of the most common applications for a moving control volume is if you're going to do a fluid analysis on some kind of moving vehicle. Okay. All right, so let's consider an aircraft engine. Okay. Right, so an aircraft engine, when the aircraft is in motion, is moving. Okay. All right, so let's kind of draw it out first. This will also be our first example with multiple inlets. Okay, so here is our engine here. It has an intake valve. There is an intake face here where the airflow is coming in. You have a valve here for the fuel. And it's all coming out to the outlet down here. Okay. All right. So on this, in this figure here, we have fuel that's coming in here. Okay, so the fuel is coming in with some mass flow rate, so that's coming from the airplane itself. Okay, and since the airplane is moving, this entire engine is also moving as well. Okay, so what we're going to say is that this entire control volume here is moving with the velocity of 971 kilometers per hour, and it's moving from the right to the left. Okay. All right, and so let's also label this, and so we'll call the inlet face, we'll call that face one, call the outlet face face number two. Okay. Let's say we know the inlet area, so the inlet area of the face here is 0.8 meters square. The density of the air at the inlet is 0.736 kilograms per meter cubed. And then at the outlet, our outlet area is 0.558 meters square. Our density at the outlet is 0.515 kilograms per cube. Okay. This will also be our first problem where the density actually is going to change from the inlet to the outlet, so it's no longer a constant. Okay. But control volume analysis really excels in these types of problems here, right? Because inside this inside this aircraft engine, there's some mixing of air and fuel that's going on. There's maybe some compressibility effects that are going on, and so that's why our outlet fluid has a smaller density. But control volume analysis is actually able to handle these types of situations, unlike Bernoulli equation. So this example is great and well. Okay, another thing that we notice is that fluid is actually, or air is actually coming out from the outlet as well. And so what we can say, and let me just be consistent, we'll call this V2. Okay. So let's say that, we are an observer on the ground and somehow we have the eyes of, of Legolas and we can kind of see the fluid, the velocity of fluid coming out of an airplane, right? And so let's assume that we know that the velocity of fluid coming out has a velocity of 1,050 kilometers per hour. Okay. And then in the problem, what we say is that this velocity here is as observed from a fixed reference point on the ground. Okay, so that caveat there is important, and that's kind of why I wrote it out. And a lot of times, when you're doing these types of problems, that's how it's worded. Okay, and so what that tells us is that this V2 here, this velocity at the outlet, this is what we call an absolute velocity. Right, and so that velocity there is relative to the ground. It's not relative to the control volume itself. So when we plug in, right, so when we plug into our equation up here for conservation of mass with a moving control volume, this V2 is going to be plugged into this term right here, exactly, right? Because that term right there, that's the fluid velocity from a fixed reference frame, which is exactly right. Okay. All right. So with all this given information here, I know for this problem it was a lot. Let's solve for the mass flow rate of fluid. All right, so a lot of numbers here, a lot going on, but what we're solving for is just kind of one singular one. All right, any questions on just the setup for this example here? Okay. All right, so let's go ahead and apply Reynolds transport theorem to this problem here. Okay, so let's apply our Reynolds transport theorem and let's apply it to conservation of mass for this problem here. Okay. And let's also make note that we have a moving control volume. Okay. All right, so let's go ahead and write out our full Reynolds transport. So we have partial t of integral rho dv plus integral rho v minus vcv with n hat dA, all equal to 0. Okay. All right, so let's simplify this first. Okay. So this problem doesn't say so explicitly, but it also doesn't really give you a reason to believe that any air or fuel is accumulating within the engine itself. Okay. And so we can kind of infer just based on the problem, just knowing that this aircraft engine, is probably the aircraft's already in motion. There's no acceleration or deceleration occurring, and so we can basically assume that this flow is steady, right? And so if our flow is steady state, that means our accumulation term or our time derivative term here is equal to 0. Okay. So keep in mind for this problem here, I cut out all the text. I kind of just drew the figure for you guys. But usually these problems are accompanied with some kind of paragraph or text description in terms of what's going on in the problem, right? And so unless that description or unless the problem kind of explicitly states that air or fluid is accumulating within this control volume, or unless it's saying it's depleting, unless it explicitly says so, then most of the time you can assume that it's steady. Okay. All right. And so all that leaves us with is just our inflow and outflow term. Okay, so we only need to evaluate just that term over there. Okay. Now keep in mind, right? So just like I mentioned it in the problem, there are two inlets here. So we have the inlet face for the air that's coming in, the intake, the intake of air. We have the fuel that's injected as well, and then we have the output. Okay. All right, so let's go ahead and simplify this. Okay. So remember, when we apply our Reynolds transport here, the dot product with the normal vector changes the sign of our terms, right? So remember, for inlet terms, we have v dot n is less than 0, and then for outlets, we have v dot n is greater than 0. Okay? So inlets have a negative sign, outlets have the positive sign. All right. And so what we have here then is we have our two inlet faces are face 1 and the part where the fuel comes in. Okay. We have minus rho 1, A1, E, V1 minus VCV. Right, so this is the inlet face 1. Okay, next we have the fuel, right? So the fuel in this problem is actually given in terms of a mass flow rate, where mass flow rate, remember, is just density times the area times the velocity. Okay. So we're just going to subtract m dot fuel. And then finally, we have the outlet phase. And so the outlet phase, we have a plus rho 2, A2, B2 minus VCV. Okay. All this is equal to 0. Okay, good. All right, so again, so this is our first time having multiple inlets. And so when you have multiple inlets, multiple outlets, you have to make sure that you account for that in your term. Okay, so you should have one term or one expression for each inlet or outlet in your system. Okay. All right. So from here, it's pretty easy to kind of solve for this. And so remember, we're solving for m dot fuel, right? And so if we just move that over to the other side of the equation, get m dot fuel is equal to rho 2, A2, B2 minus VCV, okay, minus rho 1, A1, B1 minus VCV. All right, and so now all we have to do is just plug in for everything on the right there. But this is where things get a little bit tricky, because in terms of how we interpret each of the velocities here and what sign that we pick for them, it can be a bit tricky to kind of choose these things. Okay, so we'll kind of just go one by one. But at the very least, we have an expression here for m dot fuel. Okay. All right, any questions on this so far? How we got to this point? Okay. All right, so let's go through each of these, right? So let's first take note that rho 2, A2, rho 1, A1, those are all given to us in the problem, right? And there's no ambiguity in terms of sign. So all of those terms are positive. So all of those are still good. Okay. All right, and then let's go one by one and let's talk about each of the velocities, and let's talk about kind of what we're going to plug in for each of those. Okay. Okay. So let's start at the inlet face, actually. Okay, so that one's actually a bit of interesting. Okay, so let's start with V1. Right, so V1 there, remember, that is the absolute velocity of the fluid at the inlet as observed from a fixed reference point. Okay. I know it's always a mouthful whenever you're talking about different reference points and different kind of perspectives. But I'm going to try to be as detailed as I can here, because I think again, just this part does get a bit confusing. Okay, but even if during the lecture right now it doesn't seem to kind of make sense in terms of what sign to pick and what terms are zero or not, just try to write everything down, and then when you're doing your homework, kind of go through kind of what we talked about, everything that you wrote down, and hopefully then it'll start to come. Okay. Okay. All right. So let's talk about what's happening at surface 1, right? So I'm going to scroll back up to the figure. All right. And so in the problem here, we're not given any velocity at surface 1. Okay. Because one thing that's kind of implied is the fact that our control volume, our airplane, is moving to the right, or excuse me, moving to the left with a certain velocity. Okay. So as the control volume is moving, that control volume is colliding with the air that's in front of it, right? And that air, right, if you think about a typical airplane, right, the air that's in front of an airplane, that air usually is not really doing anything unless there's any kind of turbulence or weather patterns, right? So in front here, we have still air, basically. Right? We have air that's just kind of minding its own business. It doesn't have any velocity, but our control volume is colliding with that still air. Right? But from a fixed reference frame, right? And so if we were to stand on the ground from a fixed reference frame and look at the air that's in front of an airplane, right? And let's assume kind of perfect conditions, right? We can say that that air does not have any velocity itself, right? And so we can say that V1 is actually equal to 0. Okay. Right. So even though there will be velocity that's coming in, right? And so if you run at full speed down, down the street, right, you're going to feel wind blasted in your face, right? But that doesn't necessarily mean that the wind is blowing. It's just that you're moving towards the wind, right? And there's wind that's coming towards you because you're moving towards it. Okay. But from a fixed reference frame, the air in front is actually not really doing anything. Okay. Okay. Now let's look at VCV, and this is gonna apply for both of these terms here. All right. So we know from this problem that the control volume is moving from right to left with a velocity of 971 kilometers per hour. Okay. All right. So that seems pretty obvious, right? So it seems like we would just plug in 971 into that, into that term right there, right? But and but you do have to account for the direction of the velocity. Okay. Okay. And so the fact that our control line is actually moving to the left actually does play an impact, right? And so if we draw our positive x-axis going to the right, as we typically do, right? Right. So positive x direction is usually moving over to the right, just like that. Okay. So that means what we actually plug in for VCV, even though the problem gives us the absolute value of the speed, right? And for our equation here, we actually have to take the direction into account. Okay. Right. So the fact that our control line is actually moving to the left, at least in terms of how we drew it, that means what we plug in actually is going to be a negative 971 kilometers per hour. Okay. Because if you look back at our Reynolds transport, right? So let me kind of scroll back up here. I know we kind of plugged in for it here. Okay. But if you look at these two velocity terms in our Reynolds transport, right? These are velocity vectors, right? And so vector, a lot of times when we do vector algebra or vector math here in fluids, we typically ignore the vector. But in this case, it actually makes a difference, right? And so that makes a difference in terms of the sign. Okay? Right. So don't lose that detail. And in fact, it gets confusing because you also have to keep in mind the sign convention of the inlet versus outlet that comes from the dot product as well. Okay. Right. So there's kind of multiple sign conventions here that you have to kind of keep track of. Okay. So just kind of keep that in mind that there are multiple sign conventions that you have to kind of keep track of, right? This is definitely the most confusing part of this is just, keeping track of all the different signs and kind of what to plug in for. Okay. Okay. And then the last term that we have to plug in here for is V2. Okay. Right? So V2 there, that is the absolute velocity of the fluid at phase 2 as observed from a fixed reference point. Okay. Right? So same definition as V1, but we have to take the same sign convention that we took into account for in the previous part as well. Okay. Because technically, if you look at that term in our Reynolds transport, that fluid velocity also has a sign convention too, because it's a vector. Okay. Okay, so with that in mind, let's go back to our figure and let's see which direction that V2 is pointing. Okay, so we go back up to the figure here, right? We see that V2 here is going from left to right, right? So V2 actually is already pointing in a positive direction, right? So we don't need to flip the sign here. Right, and so with that, we can say that V2 is equal to a positive 1050 kilometers per hour. Okay. Right, because its vector sign is pointing to the right. Okay, so lots of little different rules, lots of little different sign conventions, and so I know it's a lot, right? It's a lot to kind of keep track of. But that's why I think it's always helpful for these problems. Write out kind of as much as you can. Try to reason with yourself in terms of what sign should this be? Should this term be 0 or not? Don't be afraid to kind of write out your reasoning, just like this problem here. That way, when let's say that you make a mistake, you can go back and you kind of remember and kind of work your way through in terms of, maybe I made a mistake with this sign convention right here. Okay, so don't be afraid to kind of write out every step, every single part of your thinking, because there's a lot to keep in mind here with control volume analysis. Okay. Okay, so plugging it all in. Right, because we have everything we need here, so we can say that m dot fuel is equal to. Okay. All right. So we have rho 2 A2. So rho 2. Let me just get the numbers for that just again. Want to leave this page right here. Okay. Okay, so row 2, as given to us in the problem, was 0.515 kilograms per meter cubed. Okay. This right here is row 2. Okay. A2 as given to us in the problem was 0.558 meters squared. This was A2. Okay. All right, next we have V2 minus VCV. So V2 we know is 1050 kilometers per hour. Right here, V2 minus a negative 971 kilometers per hour. Okay. All right, so this is VCV. Okay. All right, so that's the entire first. That's the entire first term there. Then we have everything from the inlet face. Okay. So from the inlet face, we have row 1. So row 1 is 0.736 kilograms per meter cubed. Okay. So this right here is row 1. A1 here is 0.8 meters squared. We have 0. Remember, our fluid is at rest at the inlet face as observed from a fixed reference point. But there is actually inflow because our control volume is moving. Do a minus 971 kilometers per hour. And this again is VCV. Okay. All right, so you put it all together. There is a little bit of conversion that you have to do here. Just noting that our speeds here are in kilometers per hour, but our area and our density there is given by meters, right? So just be careful about that. Okay. So I'm not going to do the conversion here just because it's, we kind of spend enough time on this example, but you plug everything in, you convert everything properly, and what you get is that the fuel must be injected at a rate of 9,100 kilograms per hour. Okay. So there's a lot going on in that, and yet that, somewhat deceptive, simple problem, right? There's just a lot of sign conventions, a lot of, nuances and kind of things to account for with the moving control. Okay. Yeah, so this is definitely an example I think that you guys will be returning back to, again and again while you are, doing your homework, so studying for the exam. So this one is a really good one because this one kind of explains almost everything. Okay. All right. Any questions on this example? Anything that we did? Okay, good. All right, so next let's do deforming control volumes, okay? Which thankfully are actually a lot simpler. So now that we have this background for moving control volumes, deforming control volumes will be a lot simpler to do. Okay, so deforming control volumes are problems where our control volume itself is actually going to be changing shape or changing size. Okay. So again, this is not a type of problem that you'll see all too commonly. But for certain types of situations, it is kind of the most natural way to analyze it, right? Because a lot of times you'll have situations where your control volume or just your subject or your the geometry for your problem is naturally going to be changing size or shape. Okay, so some examples, maybe you're looking at the inflation of a balloon, or maybe you're looking at the liquid inside a syringe. Okay, right? There will be lots of situations that account for this. Okay. Okay. So for these types of problems here, we actually use the same Reynolds transport as our movement control volumes. Okay. So we're going to use the same equation, but how we actually apply it will be a little bit different. Okay, so let me go ahead and write everything out again. So first we have our accumulation term. So our accumulation term is partial t of rho dV plus integral of rho v minus vcv vector dot product of n hat dA, everything equal to 0. Okay. So in these types of problems, even though the control volume itself is likely not going to be moving as a whole, but certain boundaries or certain locations within the control volume may be moving with the velocity just based on how the control volume is deforming. Okay. Now I will say, we're not going to do too much with this, just because these situations are a lot more niche, right? And so we're just going to do a very simple example, but I do want to kind of mention kind of how these problems change a bit. Okay. Okay, so the main difference that you're going to see here is your accumulation term is going to be non-zero. At least 99% of the time. Okay? I can't think of a case in my head right now where you have a deforming control volume where the accumulation term is 0. But there might be some situations where that's the case. Maybe a problem that's deforming equally on both sides. But for the most part, this term here is going to be non-zero. And the reason for that is that when you are doing these problems, the volume of the control volume itself is actually going to be changed. Right? So it makes sense that there's going to be either an accumulation or a depletion of fluid within the domain. Okay. Okay, so that's the only consideration here. I think once you see an example, it'll be kind of clear in terms of what needs to be. Okay, so let's do a simple example. This one will be much simpler than the previous one, partially just because we've gotten most of the explanation of the relative velocity out of the way. Okay. So let's look at the case of maybe we have a syringe filled with medicine. Okay. Right. So this is an area of fluid mechanics that I think people don't really think about. But this is a very important area, right? So this is what I consider to be microfluidics, right? So you have very small amounts of fluid moving in very, very small channels or very, very small spaces. Right? Okay. So let's say we have a syringe here. Maybe something like this, right? So this is a typical syringe. And so if you've ever seen a syringe before, you'll know that there is a region of the syringe where it's basically just a graduated cylinder filled with some kind of fluid, usually medicine, and then the fluid comes out through a needle. Okay. All right, so let's say that we have a situation here where we have a plunger. So that's the part where you kind of push down and kind of push the liquid out. Okay. And let's say that plunger is advancing at a constant velocity. right? So let's say that the plunger is advancing with a constant velocity, which we'll call v. Okay, and so we are going to define, we're going to eventually compute what VP is. Okay. All right. And then at the plunger side, let's say that we have a area. Okay, so the surface area of the plunger will be 500 millimeters squared. Let's say that the two portion of the syringe here has a length L. Let's see. Have L here. No, we don't. But it is going to be cheap. All right. And let's say that we know just based on the problem or just based on our observations that medicine will be leaving the syringe here at a rate of 300 milliliters per minute. Right? So in other words, we know the volumetric flow rate of fluid at the exit here. Okay. See any other information that we have here? I think that's everything. Okay. And so based on this problem here, what we want to do is want to compute. Okay. We want to compute the speed of the plunger, Vp. Okay. Good. All right, so fairly simple problem here, and it may seem fairly contrived, but this actually has a lot of practical importance, right? So actually last summer, my son actually spent a lot of time in the hospital, and he had to take a lot of medicines. And one thing that they had to regulate was, how much medicine that they were giving my son at any given time, right? And they had these machines, and so I'd never seen them before, but it's a very standard hospital machine where they kind of they pull up the medicine in a syringe and they put it in this machine where the machine is able to kind of push the medicine out, and they have a plunger that moves at a very specific speed. Okay. So let's say that, you're an engineer, you're designing that machine, being able to correlate, what speed that you should, turn your actuator at, turn the motor at, compared to how much medicine that needs to come out, this is something that's a very important design consideration. Okay. All right. So this problem here is very much kind of inspired by that. Okay. All right. So with that said, we have a situation here where, this fits very well with the deforming control volume. Okay. So since the plunger is advancing, right, the region where the region that is occupied by the fluid is constantly decreasing, right? And so we can draw our control volume to kind of move along with that plunger surface. Okay. So, I realize I haven't really been doing this for the problems, but, one thing you should be doing for these types of problems is you should always be drawing your control volumes. Okay. So I'd say for the last three examples we did, it was fairly obvious in terms of what the control volume is. But when you have a situation like this where the control volume is deforming, it's a good exercise to kind of draw what. Okay. Okay. So remember the control volume, usually you're going to draw to encompass all the fluid in question. So control volume like that is adequate. It's fine. Okay. Where we know, just based on the problem, that as the plunger kind of moves from left to right, this surface of the control volume is going to start to move inwards. Okay. 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 All right. So now that we have everything, we've kind of established everything. We know what our control volume looks like. Let's write out our Reynolds transfer. Okay. Partial t integral rho dv plus integral rho v vcv dot n dA. All to zero. Okay. So next we need to kind of evaluate each of these integrals here and kind of find out what they look like. Okay. All right, so first thing we're going to do is we're going to make note, since, unlike the previous problem where we had compressible air and we had kind of a mixture of air and fuel, right? This right here, we have just a single fluid within our syringe. Okay? In fact, it's an incompressible fluid. So let's take our density, right? Since density is going to be a constant for an incompressible fluid, let's pull those out. Okay. Right? So since density is a constant, we can pull it out of all the integrals, we can pull it out of the time derivative. And since we're doing conservation of mass, and the right-hand side of this equation is zero, right? For a constant density, we can essentially just cancel it out. So that's nice because the problem actually didn't even give us a density, right? And so that's kind of a hint, the fact that we don't need it, but it's good to kind of do that. All right, and then what we're left with here is we have partial t. Okay. We have partial t of the integral of dv, right? And so if you kind of recall, I think it was the second example that we did last Thursday, right? When you have integral of just dv, all you get from that is just volume. Right? So when you're taking integral of one dv, then you just get the quantity that you're just integrating. Okay. Good. Another thing that we'll make note of in this problem is the fact that we actually don't have any inlet, right? So there's no fluid being added to the syringe. In fact, fluid is being expelled from the syringe. Okay. So there's no inlet phase, but we do have an outlet. We have no inlet with a single outlet. In fact, we have a very simple case here where our single outlet, right? At our outlet face, our control volume is not moving, right? So that region of the control volume is not actually moving. The only region that's moving is the left side with the plunger. Okay. Okay, and so with that said, what we obtain from this after we evaluate the integral is we get plus Q2. And so at the outlet face, we have VCV is actually equal to 0 at that location. Okay. And so when we evaluate V dot N dA, right? Right, we account for the fact that this is an outlet, and so that tells us that the dot product with respect to N is going to be a positive number. Remember that dot product there is negative for an inlet, positive for an outlet. Okay. And so since we have a positive, then we have just basically just velocity multiplied by the area, right? Integral that. Right. And so doing that, assuming that our velocity is constant along that syringe surface, or I guess technically you don't have to. We just get the volumetric flow. Okay. Okay, so that's kind of how we simplify to that expression there. Okay. Good. All right. Any questions on this so far in terms of how we got this expression? Okay. All right. So from here, it's pretty straightforward. Okay. The only other thing that we have to do here is we just make note of the volume. Okay. So the way we drew our control volume here, we basically drew our control volume as if it were a cylinder. Right, and then how do you find the volume of the cylinder? The volume of the cylinder is just the surface area of the cap multiplied by the length, right? And so the volume of our CV in this case is AP times L, right? For AP there, that's the surface area of the plunger, and L is the length of syringe that is occupied by the fluid, right? Okay. Right. Next thing we'll make note of is the fact that, our plunger is moving from left to right. Our plunger is not expanding or contracting, okay? And so throughout this entire process, right, throughout the entire process of the syringe pushing the fluid out, the cross-sectional area or the surface area of the plunger, this is going to remain constant. Okay. All right, and so if we plug this expression for the volume in, and just noting the fact that our plunger area is constant, that means we can pull it out of the derivative. Okay. Okay, so we have partial T of the volume is equal to partial T of AP times L. Okay. Right. Surface area of the plunger here, it's constant, so we can just pull that out. Right? So we have AP multiplied by partial L, partial T. Okay. Where partial L, partial T, that is the rate of change at which the length of our control volume is changing. Okay. Which we have an expression for, right? So since our control volume is deforming along with the plunger, right? The rate at which the length of the control volume is changing is actually the velocity of the plunger itself. Okay. And so what we can do is we can replace this with VP. All right, and so with that, we can just plug that in, and then we have everything that we need to go with this problem. Okay, all right, so we plug that in, we get AP times VP plus Q2 is equal to 0. Therefore, VP is equal to minus Q2 divided by AP. Which you're going to get a negative number for this, but in this situation, this is one where we can just ignore the sign. Okay. And so we plug in for that, we get 60 centimeters per minute. The reason we get a negative here, if you kind of want to be specific, is the fact that our volume is actually decreasing, right? And so that VP there is the fact that, or the negative in the VP there is the fact that our volume is actually decreasing at this rate, okay? But in this problem here, we're only looking for the speed, and so that's why we can just ignore the sign and say the velocity is 60 centimeters per minute. All right, any questions on this example here? Okay. All right, so it's 4:07. Let's take our break a little bit early just so I can give you back your exam. So I'm going to go and put the exams here. We'll pick it up again at 4:20, and then we'll go on to momentum from there. But if you want your exam, they are right. Okay. So the exams are rated out of 50. Please take a look at your exams. I try to leave as many comments as I can what I could whenever I took off points. If you do have questions in terms of how it's graded or you want to look at it again, I'm always happy to do so. Just let me know. And so the deadline to get regrades on the exam will be next a week from today, so next Tuesday. Right, it's 4:20, so let's get back into it. Okay, all right. So we just finished our discussion of conservation of mass with the Reynolds transports. We did quite a few examples here. So we did two examples last Thursday, two more today. With these types of problems, there's just kind of have to keep doing examples and looking and see how things are done. There's a lot to keep track of, honestly. There's a lot of kind of nuance, there's a lot of kind of rules, especially with sign conventions. And you'll see it's going to get even worse with momentum. And it's maybe a little bit worse, but not as bad with energy that we're going to do tomorrow. So with these, with these sections here, I try to just jam pack as many examples as I could, that I could write down. And if you did happen to pick up the textbook, there's more in there as well. So I definitely recommend looking through all the examples we do in class. Looking up more examples in the textbook. There's more examples that you can find online as well with control volume problems. You just kind of have to just keep exposing yourself and keep looking how things are done. Because there's honestly just a lot that's going on. Okay, so let's go ahead and move on to the next application of Reynolds transport, which is conservation of linear moment. Okay. All right, so this will be the first time that we're applying Reynolds transport to something other than conservation of mass. And it does actually make a difference. Okay. Okay. And so the first thing that we'll go over here, independent of fluids, let's remind ourselves of Newton's second law. All right, so if you recall from your mechanics class, dynamics class, basically the rate of change of linear momentum of a system, okay, is equal to, right? So the way that you change the momentum of an object, of any object, a solid object, is to apply an external force, right? So the time rate of change of linear momentum for an object is equal to the sum of external forces acting on that system. Right? So if you have an object, you want it to start moving, right? You apply a force to it, right? And same thing goes for fluids as well. So for the first time, this means that we actually have a way for us to actually create momentum and even destroy momentum at the same time. So even though momentum is a conserved quantity, right? It's not like mass, where mass it's literally impossible to create or destroy any mass. Okay. If we want to create or destroy momentum, we have to apply an external force. All right. So with that said, we can alter our Reynolds transport theorem to account for this fact. Okay. Okay. So let me go ahead and write out the Reynolds transport theorem for momentum, and then you'll see how it actually changes from there. Okay. All right. So just like in mass, we have our accumulation slash depletion. Right, so accumulation slash depletion, that is different from production. So accumulation slash depletion is either the accumulation or depletion of our quantity within the control volume itself. Okay. Okay, and also the subject of this of momentum is, well, momentum. It's not mass anymore, right? So what we actually plug in for RTT is going to be different. Okay. Now I know up until this point, for the last couple lectures, we've been applying RTT to mass. And so, implicitly that means that we're plugging in just one for little b. But remember, Reynolds transport theorem we can use for any quantity that occurs within the fluid, but we do have to adjust our RTT to account for that. Okay. All right. And so our expression here is partial t integral of our velocity. I'm going to give the velocity symbol u here just to kind of differentiate it from the other velocities. Okay. So this u right here, this u vector, is what we're going to call the momentum velocity. That's not the official name for it, by the way. That's just the name that I kind of give it. But I think it's important to differentiate it with the other velocity that comes in our inflow and outflow term. Okay. Okay, speaking of that, let's go ahead and write that out, right? And so just like RTT for mass, we also have an inflow and outflow term. But this too needs to be adjusted for momentum, right? And so this is going to be integral. Oh, excuse me. I'm sorry. There's also a density here as well. I was forgetting something. Okay. So don't forget that density there. This one also has a density multiplied by u. Okay. So once again, we have our momentum velocity. And it's going to be multiplied by v dot n. And so that v there is the same as it was before. So it's again, this u here is what we call the momentum velocity. And then this v, right? The velocity that is being dot product with the normal vector here. This is what I call the carrying velocity. After we write this down, we'll kind of differentiate between the two. Okay. Okay. Now, the other big difference with momentum is that normally if we were doing this for mass, all this would equal to zero because there's no way for us to create or destroy mass. But we know from Newton's second law that we can actually create and destroy momentum. And the way we do that is by applying external forces. So this is going to be equal to the sum of all external forces onto the system. Okay, so there is our Reynolds transport theorem for momentum. Okay, so a couple obvious differences with mass, right? First of all, we have an extra velocity term that we need to integrate in both the accumulation and inflow-outflow terms, right? So we have the momentum velocity that's there. We'll see how to deal with that in the example. And then our right-hand side, instead of being zero, we're set equal to the sum of external forces. Okay. Okay. So a few notes before we kind of jump into an example here. So this is kind of the pure form of Reynolds transfer for momentum. But for this class, just for the sake of simplicity and just otherwise these problems just get really complicated. In 99% of the time, actually I can say with certainty 100% of the time, for momentum problems, we're going to assume that the accumulation depletion term is actually going to be equal to zero. Okay. So there's good reasons for that, and actually the reasons are kind of explained more in the lecture notes. But just for the sake of simplicity, and even for all the examples we're going to do today, we're going to assume that accumulation term is zero. Because as you accumulate momentum, or if you start to kind of decelerate and kind of lose momentum, then you start to get into kind of non-linear type problems where it gets very complicated. So for our sake, we're basically going to assume steady state for all of these types of problems. Okay. Okay. I think I'll wait for the example to talk about the difference between momentum and carrying velocity. I think it's a bit easier once you kind of see it. But one other thing that I'll note before we get into the problem is to talk a bit more about these external forces. Okay. All right, so whenever you have a situation where you have flow either speeding up, slowing down, or even just changing direction, there needs to be a force that's being applied on the flow from some. even in simple situations that we've seen before, right? So, we looked at the simple situation of a nozzle, right? We know that from a nozzle, just from a conservation of mass perspective, right, the flow has to speed up as it goes from the wide end to the narrow end of the nozzle, okay? What we haven't talked about is that, in order to produce that speed up, the nozzle is actually exerting force onto the fluid, right? Which may seem kind of strange because a nozzle seems like a very passive device. But there are reaction forces within the nozzle just associated with the change of direction and the change of velocity of the fluid that causes that speed. Okay. So whenever you have a change in velocity, either speeds up, slows down, or changes direction, there has to be a force from somewhere. Most of the time, it's going to be some kind of reaction force from a solid object that's contacting the flow. But there are other mechanisms to apply forces as well. So things like pressure forces, friction, weight, things like that. Okay, so I mentioned that first, just because I think this momentum is kind of one of those things where it gets very easy to get lost in the details of these problems. And so I don't want you guys to kind of lose the big picture in all the details, right? So kind of the most important thing, from this is to just realize and just remember that whenever flow is either changing direction or changing speed, there has to be some force that is causing that change. Okay. And then once you kind of think from that perspective, it actually frames the problems in a little bit of an easier way. You start to think, where is this force coming from? And it becomes easier to compute it from that sense. Okay. All right. Any questions on this before we jump into an example? Okay. All right. So let's do a very simple example first. I say simple, but this is probably the example we'll spend the most time on for the second half of class today. Okay. Okay. So let's consider just a simple redirection. So let's say we have a flow that's coming in, it's hitting a ramp, and then it's changing direction as the flow kind of flows along the route. Okay. All right. So we have a fluid jet. Use blue for that. So let's say the fluid jet comes in at a certain velocity u1. Okay. Right. It's completely horizontal. Let's say that this jet hits a ramp. Right. So the ramp kind of looks something like this. And the ramp kind of redirects the flow upwards. A little bit of a departure from the previous two examples. This one's kind of a bit more contrived. It's not really kind of a realistic example. But we have to start somewhere. And then after this, we'll get to more realistic examples. Okay, so as a result of the ramp, then the fluid also must change direction as well, just because the fluid just can't phase right through the ramp itself. Okay. Okay. And so the fluid is just simply changing direction and it's going upward just like that. Okay. All right, so let's go ahead and draw our control volume here. Remember our rules for control volumes. We want to draw the control volume such that the flow is always perpendicular to the surface of the control volume. Okay. That's why I drew this kind of upper right surface here with this direction here, just so that the fluid can exit perpendicular to it. Okay. All right. And then one other piece of information we know. Let's say that we know the direction of the outlet jet. Okay. Okay, and so let's say that the outlet jet there makes an angle theta with respect to the horizontal. Okay. And so for this problem, we're just looking for something very simple. Okay. So this ramp here is fixed to the ground. And so all we want to do in this problem is we know that there has to be a force that the ramp exerts on the fluid, right? Otherwise, it wouldn't be able to change direction. Okay. And so that force, an equal and opposite reaction force, is going to be applied to the ramp as well. Okay, so what we want to do is we want to compute. We want to compute the reaction forces from the ground on the ramp that's needed to keep the ramp stationary. Or in other words, we're computing what's called an anchoring force. All right. And so just like, just like we just talked about, we're going to assume that we have some state. We also need to assume we're also going to neglect viscosity and we're going to ignore gravity effects as well. Okay. All right, so fairly simple problem, but we are going to go quite in detail with everything, just to you kind of know everything that's going on, especially the momentum part. Okay, but before we start, are there any questions just on the setup for the problem? Everyone got the figure for the problem in the notes? Okay, all right, so let's go ahead and start. Okay, so first thing that we're going to do, and first thing that you're going to do in almost every momentum problem, is actually you're going to start with conservation of mass. So, if you come up to a problem, a control volume problem, and you don't know where to start, start with conservation of mass. And that's going to be true tomorrow too, once we go through conservation of energy. And so the starting point is always conservation of mass, just because it's the simplest to evaluate. Usually you're going to find something, whether it be a velocity or an area or something like that, that you can apply to the rest of the problem. Okay. Okay, so let's go ahead and write out conservation of mass first. Okay, so there's our conservation of mass, right? So same as what we did in the first half today. This is for a stationary control volume, so we don't have any control volume movement, although we will get there today. Okay, so first thing we note is that our accumulation term is 0 because we are in steady state. All right, and then we just have the inflow and outflow terms, okay? All right, so we have rho out times V out, A out, minus rho in, V in, A in is equal to 0. Okay. One thing to note here, although this is something that you'll kind of do automatically, it's something that we've already done as well, right? So remember, when we drew the figure for our problem here, we drew the control volume, we drew this upper right surface here such that it's perpendicular to the flow, okay? Remember, the reason we did that is when we evaluate this dot product, we get just, either a positive or negative number. Okay. That note ended up being a little bit longer than I thought, so the writing's a little bit small, right? So remember, the reason you draw your control volume that way is that when you evaluate that dot product, it's kind of simple to evaluate. Okay, you either get a positive number if it's an outlet or a negative number if it's an inlet. Okay, but if you didn't draw that control volume surface exactly perpendicular, you're going to have some trigonometry terms in here, some sines and cosines, which is typically what we do. Okay, so a little bit of a subtle point. Most of the time you're just not even going to consider it because you're going to draw your control volume smartly, but just be aware. Okay. Okay. Now for this problem, right? So conservation of mass essentially has given us this relationship right here, okay? Which is essentially the mass flow at the outlet has to equal the mass flow at the inlet. Okay. All right. All right, so first thing we'll note for this problem is that there's no reason for us to consider changes in density, right? We have just a simple stream of fluid that's hitting a ramp, right? And so there's nothing about compressibility effects. There's no aircraft engine or things like that. Okay. Usually there has to be a pretty explicit reason in the problem for you to consider density differences, like there's some compressibility or there's some mixture of different fluids. Here we just have a single fluid, right? And so with that said, we can thus conclude that the density at the outlet is equal to density at the inlet. Okay? And so if we can conclude that, we factor it out of the equation and we cancel it out. Okay? So along that same vein, and so this problem here has a little bit of gamemanship, a little bit of intuition that you need. Okay. But since there was no nozzle in the problem, right, there's also no reason to kind of assume, or there's no reason to kind of consider that the flow is going to change area as well. In reality, if you took a hose and you sprayed it at a ramp, there may be some splatter that occurs. But if your flow is kind of sufficiently laminar, then we can assume that we have kind of a smooth kind of transition of fluid that kind of goes from one end to the other. Okay. And so with that, we can say that A out is equal to A in. Usually for these types of problems, there has to be an explicit change in area. Maybe it's some kind of internal flow with a nozzle, things like that. Okay. But for this type of problem where the flow is kind of exposed to atmosphere, there's just a simple jet of fluid. There's really kind of no reason for us to kind of suspect any kind of change in area. Okay. Therefore, we can factor that area out and then cancel it out from our equation. Okay. All right. Therefore, right? Since the density is assumed to not change, the flow cross-sectional area is assumed to not change. That means our velocity is the same at the outlet and the inlet. Which makes sense, right? And so, the flow is there's no flow that's being added. There's no nozzle that's changing the area of the flow, right? The flow is just simply changing direction, right? And so by conservation of mass, it makes sense that the velocity is the same at the outlet and the in. Okay. Now, pay attention to how I kind of worded this. So I specifically said that the speed of the fluid is not changing, but we know from the problem that the direction of the flow is changing. Okay. But conservation of mass actually doesn't give us any mechanism to consider that change in direction. Okay. So to consider that change in direction in which we need an external force, we need conservation of momentum. But at the very least, through conservation of mass, we were able to see that the velocity at the outlet is same at the velocity at the in, okay? Which makes perfect sense with the situation I'm looking at. All right, any questions on that conclusion there? Okay. All right. So now that we have that conclusion, now that we apply conservation of mass, in this case, we get a fairly obvious result. But it's always a good idea to apply conservation of mass first. Okay. So now let's apply conservation of momentum. Okay. Now let's keep in mind, right? So let's keep in mind that momentum, unlike mass, momentum is a vector equation. Right? That means we're going to have a momentum equation in the x direction and a separate momentum equation in the y direction. And that's going to change how we actually apply the velocities in our equation. Okay. So remember when we first introduced conservation momentum, right? I said there are two different types of velocities we need to consider. There is a momentum velocity and a carrying velocity. That's where this kind of comes into account. Okay. All right. So let's do each direction here. So let's do the x direction first. All right. So I'm going to go ahead and cross out the accumulation term. We know the accumulation term is 0. I'm just going to focus on the inlet input. All right, so we apply our conservation momentum in the x direction. What we get is integral of u times v vector dot product with n hat dA is equal to the sum of forces in the x direction. Okay. Right, just to kind of remind you, this u here is our momentum velocity. Okay. And this v here, this is what we call our carrying velocity. All right, so again, a fairly simple expression, but a lot of subtlety, a lot of kind of, nuance that you have to kind of keep in mind here. Okay. All right, so let's kind of break this down. So if you notice from the momentum velocity, so this was not a typo, that I did not put a vector sign above that momentum velocity. And the reason for that is because this u here, the u without the vector, this is specifically the x component of the velocity, the x component of the fluid velocity that's coming into the control volume or going out of control. Okay. So that's really, really important to kind of keep in mind there. Okay. Whereas the carrying velocity does not really care about components, because remember we're taking the dot product of the carrying velocity with the n hat. Okay. And so for the carrying velocity, we don't really care about its vector components. We only really care about whether it's an inlet or an outlet. So this v dot n right here, this is specifically the magnitude of the velocity at that surface. Right, so we don't care about components for the carrying velocity. We only care about its magnitude, but we do need to apply either a positive sign or a negative sign, depending on if it's an inlet or an outlet. All right. So I'm going to show you what this looks like for the X direction. We'll do both the inlet and the outlet. But just try to keep in mind kind of all of these different sign conventions and the components and whatnot. Okay, so we'll do the X direction completely first, and then we'll do the Y direction after that. Okay. So at the inlet in the X direction, all right, so at the inlet, in the X direction, we have integral of u v dot n hat, yay. Okay. All right, so let's go ahead and evaluate what this looks like. Okay. Oh, we need the density. I always forget the density. Sorry. Density is constant, so we're just going to leave it on the outside. Okay. Okay. All right, so we have the density here. Okay. So at the inlet, right? So I'm going to go ahead and scroll back up to the figure. So at the inlet here, our velocity is completely horizontal. Okay, so all of the velocity is going in the X direction. That means the X component of the velocity at the inlet is simply just u1. Okay. Okay, so if we apply that to our equation down here, okay, so this u1 here, at least the way that we've implemented this is the X component of the velocity at the inlet. Remember, this is our what we call our momentum velocity. We're going to multiply that by the carrying velocity at the inlet. Okay, so remember, for carrying velocity, we don't care about components. We only care about the velocity magnitude, especially if we drew our control volume correctly. But we do have to account for the sign convention for inlet and outlet. Okay. Okay, so the velocity magnitude at the inlet is just a U1, right? But since we're at an inlet, we have to put a negative sign there for the carrying velocity. Okay, and then we're going to multiply the entire thing by A1, which is the area. Okay, so the inlet in this case, fairly straightforward because our flow is already purely horizontal. The only thing we just have to keep in mind is just the negative sign for the carrying velocity. Our question from the chat. So does F equal mass flow rate times V out minus V in 2 for this problem? Is this another form of the equation you wrote? No. So in this case, F is actually going to be a force that we're actually going to solve for. Right? So in a lot of these momentum type problems, the force is something that we're solving for based on the information from the velocities. Yeah. Yeah, so it's not like mass where for mass, the right-hand side of our RTT was 0. In this case, it's it's equal to the external force. And that's something we're solving for. Yeah. I think your question will be answered, I think, once we kind of get a bit further along. Okay, so let's do the same thing at the outlet. Okay. So now we're at the outlet and we're still in the X direction. So once again, let's evaluate this term here. So we have rho times integral of u times v dot n hat dA. Okay. Okay. So we still have our density, so the density is still there. All right, next we have the x component of velocity at outlet, okay? Okay, actually, instead of kind of scrolling up and down, let me just kind of redraw it here. All right, so we know our outlet has a certain speed, v2, but instead of being horizontal, it's angled upwards at an angle of theta, right? And so from the problem, we know that this is angled upwards with respect to theta. Okay. All right, so for the momentum velocity, we're going to plug in the x component of this velocity here. Okay. Now, if we use a little bit of trigonometry and we note the fact that u2 here, that is our hypotenuse. Okay. We can say this is equal to u2 times cosine of theta. So that u2 cosine of theta, that's the x component of the velocity at the outlet. And this right here is our momentum velocity. Next, we're multiplying by the carrying velocity of the outlet, right? So remember, carrying velocity does not care about any kind of vector components. We're just taking the magnitude of the velocity. but we are going to plug in either positive or negative depending on whether it's an outlet or an inlet. Okay. Right, so in this case, we have an outlet. And so here we just have a positive U2. Right, so since we have an outlet there, our carrying velocity is going to be a positive U2, right? And just U2, no sine or cosine, because remember, carrying velocity, we only care about the magnitude. And then we're multiplying by A2 as well. All right, good. All right, so now that we have both the contributions from the inlet and outlet, and so that's all we have in this problem, just a single inlet, a single outlet. Let's go ahead and solve for the force, the anchoring force in the x direction. Okay. All right, so the force in the x direction is equal to, we have our contribution from the outlet minus our contribution from the inlet. Okay, we have rho u2 squared cosine theta times a2 minus rho u1 squared a1. Okay. Right? Which of course we can simplify this a bit. We know from conservation of mass that the velocities at the inlet and outlet are the same. So U2 is equal to U1, and the areas are the same as well. So A2 is equal to A1 as well. All right, so we go ahead and apply that. We get Fx. And of course, for this problem, we don't have any numbers. We're solving everything in terms of variables. The next two examples do have numbers, though. Okay, so Fx in this case is equal to rho. I'm just going to put everything in terms of U1 squared. Rho U1 squared A1 multiplied by cosine of theta minus 1. All right, any questions on how we got that result there? Okay, good. So before we do the y direction, I do want to make a couple of notes here. Okay. And so just to get this simple result here, there's kind of a lot of detail that we had to go over. But like I said, I don't want you guys to lose the forest for the trees, right? So let's look at this result and let's see if it makes sense, right? So this Fx here, right? Technically, this is the force that the ramp is applying onto the fluid in order for it to change direction. Okay? So technically speaking, if you wanted to find the anchoring force, it would be this expression here, same magnitude, but opposite direction. Okay, so you just multiply by -1. Okay, so one kind of small, subtle tip here. Although, usually for most of these problems, I usually don't make that distinction, right? So as long as you come up with this expression here, I can kind of fill in the blanks to say that, it's for the opposite is for the anchoring force. Okay. The other thing that I want you to notice here is the fact that technically speaking, if no matter what angle that you plug in for theta there, right? And of course, we're assuming theta, just the way it's drawn, we're assuming theta is some angle between 0 and 90 degrees. Okay. So whatever angle that you plug in for theta there, you're going to end up with a negative, right? So let's say you plug in 45, right? So cosine of 45 is √2/2. That's something that's less than 1. Okay. So because of this, right? Because of the fact that this is always negative, any theta less than 90 degrees, right? So some kind of acute angle. This tells us that our fx here is going to be negative, right? And a negative fx means that it's pointing in the left direction. So in order for this flow situation to become reality, right, the ramp has to put a force on the flow in the negative x direction. Okay. And that makes sense, right? So if you think about it, right, this flow, right, it's changing directions on the ramp, right? And so in one sense, you can say that, the y momentum of this fluid is increasing, right? Because originally the flow comes in horizontally, it has no momentum in the y direction. And then all of a sudden, because of the ramp, it now has some momentum going the positive y direction. Okay. But because of that turn, that means its x momentum has to also slow down as well. Okay. So in order, okay. So for this particular situation, when you have this change of direction, that means the momentum in that x direction has to decrease. Okay. It's the same when you're driving your car, right? So let's say you're driving your car, you're coming up to a turn, right? You're turning to the right, right? Your old momentum, which used to be going in the, let's say in the north direction, right? So let's say you make a right turn, then that momentum in the north direction suddenly is going to decrease by a lot, hopefully to 0, right? So hopefully you make a good 90-degree angle turn. You're not merging into someone else's lane. And so this is kind of the same way, right? And so the momentum in one direction is decreasing, but as you'll see when we do the momentum in the y direction, that momentum is increasing. Okay. So since the x momentum is decreasing, that means our force that we're applying must be applied to oppose the flow. All right, hence why the force there is in a negative direction. Okay. All right, so we have a relatively simple result, but you can see that even from a simple result, there's a lot of really interesting analysis and conclusion that you can draw. Okay. All right, any questions on this before we do the y direction? Okay, all right, so let's do the y direction. So we're just going to do the same thing as we did before, just everything in the y direction. Okay, so for the y direction, I am going to go a little bit faster, just because we've kind of seen all this. All right, so let's do this exact same process that we did. So let's evaluate inflow and outflow terms, but now let's do it for the y component of the momentum. Okay, so first let's do the inlet. All right, so we have integral V, always forget the density, right? Density times integral V times V vector dot product with N dA. Okay. All right. So for the y direction, remember, what changes now is that we're going to change the component of the momentum velocity that we're looking at. Carrying velocity still stays the same, right? So in fact, the carrying velocity, whatever you compute for the x component, that stays the same here. Technically, the carrying velocity is the same as our conservation of mass as well. All right, so let's go ahead and plug in. All right, so we can't forget our density. All right, so for the inlet, right, at the inlet, we know that our flow is completely horizontal, right? So that means we have no momentum in the y direction at the inlet. We just have a big fat zero there. Right, and so we have a zero there. So that zero is going to cancel everything out, but just for the sake of completeness, let's fill in everything else. Okay. All right, so carrying velocity at the inlet, right? So same as our x component. Right, so we have a minus u1, right? So that minus sign there is to account for the fact that we're at an inlet times a1. Okay, but of course with the zero, this whole thing kind of goes to zero, but that's how all the terms would be evaluated at this inlet. All right, so now let's do the outlet. All right, we have rho integral v vector dot n hat dA. Okay. Let me draw our velocity vector at the outlet one more time. All right, so our velocity vector at the outlet, remember, is angled upwards at an angle of theta. Okay. So that means the y component of velocity here is going to be u2 sine theta. Just realized I made a swap from v to u, but hopefully you guys were able to catch that. Okay. All right, our carrying velocity at the outlet's still the same, so this is still going to be u2. Okay. And we're multiplying by the area at a2. All right, and so since our contribution to the y momentum is zero at the inlet, that means the only contribution from the y anchoring force is going to be from this outlet here. Okay. Okay, so therefore, the force that must be applied in the y direction is only equal to our contribution at the outlet, which is what we have here. Okay? So we have rho times u2 squared sine theta times a2. And so just like we did with the x momentum, let's look at the sign here. And so you can see that we have just a pure positive number, right? And that's of course assuming that our angle theta is somewhere between 0 and 90. And of course that makes sense because in one way that you can think about it is that we're generating momentum in that y direction, right? So we have to generate momentum there, so we have to apply a positive force in that y direction. Okay. So our sign convention makes sense in this case. All right. Any questions on that? Okay, good. All right, so let's do another example. Another example with a fixed control volume, and then maybe we'll get. We should probably be able to finish, and so then we'll do an example with a moving control volume, and that'll be it for momentum. Okay, so this example has numbers, thankfully, so it's not just variables in one. Situation is a little bit more interesting too. It's not just a ramp it's just not a fire hose with a ramp. Okay. All right, so let's consider the following test stand for a jet engine. Okay. So basically, in the situation, we are basically, let's say that we work for NASA, right? So we have this jet engine, and we want to measure the amount of thrust that it generates. Okay. Okay. So let's say we have our engine like this. Okay. All right. So right now our engine is not attached to an airplane; it's attached to the stand. The stand is of course attached to the ground. Okay. So that stand is going to prevent the aircraft engine from going anywhere, although it has to be a very powerful stand. Otherwise it's just going to break. Okay. Okay. All right. So let's see. So we have an inlet face on the left. Okay. So this will be face number one. Flow is coming in, and we have flow coming out on the right hand side, which we'll call surface number two. Okay. So at the inlet, let's say the velocity at the inlet we measured is 200 meters per second. And the inlet area we'll assume is 1 square meter. All right, and then at the outlet, we know the speed of the air at the outlet, let's say it's 500 meters per second. Okay. All right, so through the engine, basically the fluid is speeding up, right? So it's speeding up by an amount of 300 meters per second. Okay. And so that's going to create a thrust force. Okay. And so because the flow is speeding up, that's going to create a thrust force going in the positive x direction. Okay, so from left to right. All right, we're also given that at least in this testing rig, our density of air is going to be constant, and it's going to be 1.02 kilograms per meter. All right, so we'll neglect kind of the addition of fuel, and we're going to neglect any compressibility effects as well. All right, so for this problem here, what we want to do is we want to compute. Let's compute the thrust force that's generated from this engine. All right, so luckily, for this problem, as opposed to the last problem, we just have one-dimensional flow, right? So we don't have any flow in the y direction, at least not at our inlet and outlet. And so we can do everything in terms of the x component, okay? Okay. So that saved us a bit of work, right? So in that sense, we only have to apply momentum in the x direction. Okay, so just like we did in the previous problem, let's start by applying conservation of mass. Okay. Remember, every control volume problem in general, you're going to start by applying conservation of mass. Okay, even if it's not obvious, right? So even if you think, maybe we don't need it this time, almost always you're going to need it. Okay, because if you look at this problem. So in this problem, we're actually given the velocities at the inlet and the outlet, right? So we know the velocity comes in at 200 meters per second, it leaves at 500 meters per second, right? And so that's good, right? But there is actually one piece of information that is missing, which is the outlet surface area. Okay, so we don't know A2. And we do actually need that because when we apply conservation momentum, we do need A2 in order to plug in for that. Okay, but luckily we can get that from conservation of mass. All right, and so just like we usually do with conservation of momentum problems, let's assume steady conditions so we don't have to consider the accumulation term. Okay. All right, and so then we have integral of rho multiplied by the carrying velocity A is equal to 0. Okay, that means rho out, U out, A out, minus same quantities at the inlet, rho in, U in, A in, equal to 0. We know that the densities are the same at the inlet and the outlet, right? So that was given to us in the problem. So we're not considering any compressibility effects, right? So since density is the same at the inlet and outlet, we can go ahead and cancel those out. Okay. And let's see. So the quantity in question here is A out, right? So this is A2. Right, so if we solve this equation for that, we get A2 is equal to U in, A in, divided by U out. Okay. Right, so we have all the numbers for that. And so A in is 1 meter square U in is 200 meters per second. U out is 500 meters per second. So we get A2 is equal to 0.4 meter squared. Okay, good. So now that we have A2, we are now ready to apply conservation of momentum. So let's apply our Reynolds transport theorem for conservation of momentum. Okay. Once again, assuming steady conditions. So we'll assume steady conditions and, remember, we're only going to do this in the x direction. Okay. All right, and so for that, we have integral of rho times u v dot n hat dA. Yeah. All right, so we're going to need to evaluate this this expression here at the inlet and then evaluate it at the outlet as well. All right, so let's start with the inlet. So at the inlet, we have the product of the air density multiplied by the inlet velocity u1 times negative of the inlet velocity u1 times a1. Okay, where this u1 right here, this first one, remember this is the momentum velocity. Right, and so we don't have any trig here just because our flow is just in the x direction, but we do have to account for the sign of the velocity itself. Okay, but since our velocity here is going from left to right, that means we have a positive u1 in that term right there. Next, we have our carrying velocity. So our carrying velocity is also u1, but we need to have a negative there because we're at the inlet. Okay. Okay, so that's our expression at the inlet. Next, let's evaluate the same thing at the outlet. And so at the outlet, we have the product of the density times U2, both positive, times 8. Okay. Once again, we have the momentum velocity, which is the x component of velocity at the outlet, which is a positive U2. Okay. And then we have the carrying velocity, which also is a positive U2 because at the outlet, our carrying velocity is positive. Okay. All right. And so we plug everything in, and what we get is, oops. Anyway, so our force in the x direction is equal to, we have minus rho u1 squared a1 plus rho u2 squared a2. So we plug everything in, right? We have everything here that's given to us in the problem. We have the densities, we have the velocities, we have the areas. Okay, we get 61,200 newtons. All right. And once again, let's note the sign. And so remember our sign here is positive. That means our thrust force is going in the direction to the right, which is what we want, right? And so this means that we need 61 kilonewtons of force. Okay? And that force is going towards accelerating the flow from 200 meters per second to 500 meters per second. Because anytime you have a large kind of increase in velocity, there has to be a force there that has to be accelerated. Okay. And it turns out that force is also the thrust force that we generate from this engine. All right, any questions on that example there? All right, good. Yeah, so that example, went much quicker, but hopefully, you're starting to kind of see the pattern between momentum velocity and carrying velocity. Okay. All right, so last thing that I want to talk about today, which ironically is exactly where we started, is moving control volume. So I don't think we'll be able to get through everything. I'll probably introduce the concept of moving control volumes in momentum, but we'll probably do the example first thing tomorrow. Okay. All right, so we're going to end today exactly the same way we started with moving control volume. Okay. All right, so the way that we account for moving control volumes in conservation momentum is exactly the same way that we did for conservation of mass. Okay, but I would say for conservation momentum, it's actually not as big of a step up. In fact, we have terminology for it. Okay. So just like we did in conservation of mass, we are going to replace one of the velocities with a term that accounts for the velocity of the control volume, but we're only going to do that for the carrying velocity. And so just like we did in conservation of mass, we're going to replace that carrying velocity with a relative velocity. Okay. The only difference now is that we have a term to refer to the carrying velocity. Okay. All right. And so in our Reynolds transport theorem, where we have velocity dot product with n, okay. Right, we're going to replace this with v minus vcv, both vectors, dot product with n. Okay. Our momentum velocity is actually going to stay exactly the same, right? So that's kind of the tricky part with moving control volumes, is that when you have moving control volumes, you only apply the velocity of the control volume to the carrying velocity. Okay. Okay. In fact, because we're making the substitution, sometimes it's a little bit easier to actually substitute a different variable for this. Okay. And so instead of writing, velocity minus velocity of the control volume always, right? We can instead replace this with a relative velocity W. Okay? And so if you're following along with the notes, you might be wondering where W came from, right? And so actually, if you're following along in the notes, I introduced W, actually, during conservation of mass. But I think during conservation of mass, it's not really it's easier to start without it first. But for conservation momentum, it is actually a little bit easier to kind of bring this in at this point. Okay, so let's go ahead and substitute this in. Okay, so we're going to substitute this into Reynolds transport theorem for linear momentum. Okay. And then what I'm also going to do is let's go ahead and assume that we have steady conditions. So I'm just going to go ahead and neglect that accumulation term just right off the bat. Okay. Okay, and so what's left here is we still have our inflow outflow terms. We have integral of our density multiplied by our momentum velocity v multiplied by our relative velocity w dot product with n dA. Okay. And this is equal to the sum of all external forces being applied to our fluid. Okay, good. All right, the reason we use relative velocity here is that, you'll see from the problem that, relative velocity, once you kind of get used to the different reference frames, you actually start to think of things in terms of relative velocity instead. Okay. But to simplify this a bit further, let's actually make a substitution for the momentum velocity. Right, because we can actually simplify this a little bit more, just so that we're not mixing and matching different velocities over and over. Okay, so based on the definition of W, right, we know that W is equal to V minus VCV. Right, so remember that's the substitution that we changed or that we made for moving control volumes, and we replaced the carrying velocity with this relative velocity. Okay, but we can take the same expression and instead solve for the fluid velocity instead. Okay, and so if we do that, we just simply add the velocity of the control volume to both sides. Now let's go ahead and substitute this in. Okay, so the goal here is we just want to make this as simple as possible. Let's put everything in terms of just one variable instead of having multiple different velocities kind of floating. Okay, because the thing is, right? You can absolutely use this expression here, right? So there's nothing wrong with that equation there, right? So if you're comfortable with that, you can definitely use that. But I think what gets confusing here is that we have V, right? So V here is the fluid velocity as measured from a fixed reference frame. And we have W, which is the relative velocity of the fluid as measured from the control volume. So it gets a little bit confusing when you're mixing and matching different reference frames, okay? And so the idea here is to make a substitution so that we can put this in terms of just one type of force. Okay, so we plug that in, we get density times integral W plus dCV times W dot product of n hat dA is equal to sum of all the external forces. Okay, that. All right, so let's go ahead and distribute, right? And so we have basically a sum of two different velocities there. So let's go ahead and let's go ahead and distribute that through, and we'll have two different integrals here. All right, so if we go ahead and distribute that through, we have rho times integral W times W dot product of n hat dA plus rho integral VCV times W dot product of n hat dA is equal to sum of all the forces, sum of all external forces vector. Okay. All right. Let's look at that second term there. Remember, the types of moving control volumes that we're looking at, we're only considering situations where our control volume is moving with a constant velocity. Okay. There are control volumes that are accelerating or decelerating, but like we mentioned, those situations get a little bit complicated. Okay. So under our assumption here, we can assume this is a constant. In fact, it's actually independent of the control volume surfaces as well. Okay, so no matter what, we can pull it out. Okay, so we pull that out of the integral there. We have rho times VCV integral W dot n hat dA. Now, why is that significant, right? So why kind of make a big deal out of this term? Well, if we look at what's left, right? And I guess the density is included as well, okay, but density is also constant, okay? So if we look at what's left, we have integral of the relative velocity dot product with n hat dn, okay? Now, if we take a small detour, right? So if we take a small detour to conservation of mass, okay? So we look at our Reynolds transport theorem for conservation of mass, and we make that same assumption that we have steady flow. Right, we're left with the following. So we have this rho times integral, right? And this is for moving control volume. So we have W dot product with n dA is equal to 0. Okay? And so by conservation of mass, right, we know that the product of the density multiplied by the integral of the relative velocity dot product with NDA has to equal to 0, okay? And that, of course, that only works under steady condition. And would you look at that? You know, everything that we've underlined here is exactly that expression there. And so that means that this entire term here, just due to conservation of mass, that entire term there is equal to 0. Right? All right, and then what we're left with is actually a very simple expression. And so all we're left with is just the conservation of linear momentum for a moving control volume. Kind of a very long title, but you know, that's kind of the situation that we're looking at. Okay. Is all we get is just the density integral of the relative velocity multiplied by the relative velocity dot product with n hat dA is equal to sum of all the external forces vector. Where our relative velocity W is equal to fluid velocity minus velocity of the control ball. Okay. All right, so actually, you know, we end up with a fairly simple expression here. And so when we come back tomorrow, you know, we'll start with an example. I'll show you kind of how to apply this. We're going to see the ramp again. So I know the ramp, we spent a lot of time with it. But tomorrow the ramp will have wheels. And so when the ramp has wheels, then the whole thing will be okay. Very contrived situation, but you know, it's kind of as simple as I can think of. And then after that, we'll get into conservation. Okay. All right, so thank you guys for coming today. I hope you guys have a good rest of your evening. I will see you guys tomorrow. And if you haven't picked up your exam yet, go ahead and pick it up there. I'll bring the exams again tomorrow. So if you're on Zoom, you plan on coming tomorrow, I'll bring the exams again. Tomorrow will be the last day. So if you don't come tomorrow, they will be in my office. So I'll come to my office. You want this? What's up?
Are you exam solutions or no?
I could, yeah. I usually don't, but if you want me to, I can do that.
Would you prefer maybe coming into office hours instead?
No, I have them written out, so I'll post the exam solutions.
Thank you.
Yeah. They're at my house though, so probably tomorrow morning. I'll post it.
Yeah, that's fine.
Yeah. Mhm.
Oh, good question.
Sure.
When you meant balance the weight of buoyancy, you're looking at so buoyancy equals the weight of the egg plus the 0.4.
Yes.
Okay, yeah. Okay, so that's what I mean.
Yeah, so I think so. Yeah, a lot of people did this where I think they
I went straight into it.
Exactly.
Yeah,
Exactly.
I should have.
yeah. So yeah, you did in part A, but not in part.
Okay, I
Yeah.
get it. Right, thank you.
Yep.
And then for midterm two, are we gonna have the same cheat sheet? Just
Exactly. Yeah. So same rule. So one sheet of paper, both sides.
Perfect. Thank you.
Mhm.